Hello everyone. I am Denise Shane. I'm going to present systems of equations for mathematics. And they're important because guess what also happens is you end up doing systems of inequalities, which is where you shade a region. Just to give you kind of a heads up of where we're going with this is we tend to look for, when we're looking at systems of equations, we're looking for where the graphs cross. So there are three different ways to find a solution to a system of equations. One is graphically, so I'm going to present that first. Then I'm going to present another example where we're doing substitution, and yet a third example where we're doing elimination. So the very first one, I'm looking at graphing. Now, if the equations are in standard form, you would solve for y and get it into slope-intercept form. So I would take, and I did two different colors here so you can see where they are. So here are my axes. Here's my x-axis and my y-axis. Try to draw a straight line, not like me, all wobbly. Anyway, you always want to plot the y-intercept first. The y-intercept is the one that does not have a x by it. So that is where, I'm trying to get rid of the glare, it's not going to work. Okay, so this is what I'm going to plot first. I'm going to plot the -1 first on the y-axis. That's why they call it a y-intercept, because it's a y on the y-axis. And then without lifting my pen off my paper, I would use the slope of 2. Now 2 is the same thing as 2 over 1. So it's a rise of 2, 1, 2, and a run of 1. Rise 2, run 1, rise 2, 1, run 1. Now, in the event that you did this, and let's say you ran out of paper up there, you could always think of 2 over 1 as -2 over -1, because a negative divided by a negative is a positive. So instead of going up and to the right, you could also go down, which is a negative direction, and to the left. So down and to the left, down and to the left. And then once you have your dots, you're going to connect them, excuse my body being in the way, okay? You connect them, and that's how you plot a line. The difference between plotting a line and plotting a system is that you have more than one line. So now on this one, my y-intercept is 2. So I'm going to start off at 2, and then without lifting my pen up off my paper, I'm going to drop 1 and go to the right 2. That's what that slope means. So I'm going to drop 1 and go to the right 2. Drop 1 and go to the right 2. Okay? Or I can rise and go to the left also. Again, once I have my dots, I can connect those dots. Okay? And then the solution to the system is actually, perfect, another color, is right here. This is called the solution. Okay? Now, you can see that the solution to this system, let me move you up a bit. There. You can see that the solution to the system is in between some numbers. That's why graphing is not the optimal way to solve a system of equation. The other ways, substitution and elimination, are better because you get more exact answers. You don't get this, I don't know, it could be 1 1/3 and 1 1/3, or 1 1/2 and 1 1/2, I don't know. And it really kind of depends on the pixels. So that being said, I'm going to launch into the next Next method. Now, I didn't plan very well because I didn't come up with problems ahead of time. So let's see, let's say I have y equal, we'll take 2x minus 1 again. I'm going to pick something else though here for, let's say I want 3x minus 2y equals 6. So those are my system of equations right there. Let me see if I can't move you over so that you can see. There we go. There we go. Okay. So the reason why I like to do substitution here, I-O-N, is because this says y equals something. Or if it said x equals 2y equal 1, that would be good too for substitution. Because when you have one variable and it's solved for like one variable, what you're doing in substitution is you're pulling out that variable and putting that equation in. So you're basically nesting the two equations together. So when I look at this bottom equation, and since I have y equals, I'm going to get rid of that y, and I'm going to put what y is equal to in its place. So basically what I'm doing is I'm taking 3x minus 2y equals 6 and say, okay, that's y, but I'm pulling out the y and I'm putting in 2x minus 1. Okay, and then I'm going to solve. So I have 3x. This is a minus 2, so we distribute that through. So we have negative 2 times 2 is negative 4x. And we have negative 2 times a negative 1, that's a positive 2, equals 6. Then I combine like terms. I got 3x minus 4x is negative x, plus 2 equals 6. I subtract 2, moving that over. Moving it over, that cancels. I'm left with negative x equals 4, so x equals negative 4. Now, many of my students at this point say, hey, I'm done, yay, I got an answer, and it looks right because it's a whole number. Forget the fact that there's more fractions in the world than whole numbers. But anyway, so some people would debate with me because that's concepts of infinity. Anyway, but there's an x and a y in the problem. So what we need to do is take this table and move it out of the way. So what we need to do is take that x minus 4 and put it all the way back up in the beginning and compute what y is. So then I have 2 times negative 4 minus 1, that's negative 8 minus 1 is negative 9, is my y. So what that means is this systems of equations has as an answer, my x is negative 4 and my y is negative 9. Now what does that mean to have that answer? That answer means that when I plug in these numbers in for x and y, I'm going to get a true statement. In other words, they're going to be equal. If I take negative 4 and negative 9 and plug them in here and compute what it is on the left-hand side, I should end up with 6. So you should end up with two true statements. And by the way, kind of using this example, even though it's not the same equation, it's the only point that is going to be located on both lines. So it's the only one that is going to give you a true statement on both lines. If I put it in and it gives me a false statement, that means I did something wrong. Okay? So that is substitution, where you're taking one equation and putting it in for another I'm going to walk over here. We're going to do elimination, on this board here. Okay, so for elimination, it's used when you have things that are in what they call standard form. So let's say I have 3x plus 4y equals 12, and I have negative x minus 2y equals 7, okay? And there's my system. Now I'm going to do what they call elimination, okay? And notice that they're both written in standard form here. Now, the goal in elimination is to be able to add the equations together and eliminate or have a variable drop out. If I add these together, I would get 2x and I'd get 2y. My variable does not drop out. So what I need to do is take one of these equations, either the top one or the bottom, and multiply by something so that the coefficients, these things out front, are the same except for a sign change. So like I have to multiply this whole equation by 2 so that this is a negative 4, so that when I add it, y goes away. Or I can take this whole equation and multiply by 3 so that we get negative 3 here. And when I add it, the x goes away. So whatever you want to do, I'm going to eliminate y just because I chose to eliminate y. So that means I'm going to take this equation right here. And if I'm eliminating y, I need this to be a 4 with a negative, because we got a 4 with a positive here. I need a 4 with a negative here. So I'm going to multiply by 2 here, and what I do to one part, I have to do to all of them, right? All right, so what I end up having, this top equation didn't change. 3x plus 4y equals 12, okay? What changed is this bottom equation. So it's negative x times 2 is negative 2x, and negative 2 times 2 is negative 4y, and we always have to do the other side too. 7 times 2 is 14. Now when I add those together, okay, it's also called addition method, so you're adding. When I add those together, I get x, because 3x minus 2x is just x. This goes away, which is why it's called elimination also, because it eliminated that variable. How did it do that? Because you had a plus 4 and a minus 4, which end up being 0. And when you have 0 times y, it's 0, so the whole thing drops out. Equals 26. So x is 26. Then you take x and plug it back into either equation. So you're going to take it and plug it back in. So I'm going to have, let's see if there's enough room to do this part of the problem. Hold on. Okay. So we've got negative x is 26, so negative 26 minus 2y equals 7. Add 26 to both sides. We end up with negative 2y is 6 and 6 is 12, 13, 33, right? That's what that is, right? And then you divide by negative 2. And we end up again with a fraction now. So the coordinate that works here for both of these is 26, that's my x value, and my y value is negative 33 over 2, which is what, 16.5, negative 16.5. Normally I don't do decimals, but that's such a nice one, that should work, okay? So those are the three methods to solving systems. Let me put my face in here so you know who I am again. Those are the three methods. One is graphing, which is the least accurate and really depends on the type of calculator you have. The second one is substitution, where you're taking one equation and sticking it into the other, solving for a variable and going back. And the third one is adding them together. Now, based on the problem setup, you'll know which one to do, because if this was solved for, let's say this was solved for x equal to y plus 7, that would be something that I would probably do substitution for, because if you've got a variable by itself on one side, it's a lot easier to substitute. If you don't, then you have to put them in standard form and do addition or elimination. Okay? So please feel free to email me if you have additional questions. I also want to say that with the graphing one of the things that we will be doing, and just to give you a heads up as to what we're doing right now we're doing a similar thing where we're graphing a line. The difference is now we're picking a point that is not on the line. You know, we have inequalities, so let's throw this in there too. Let's say it's like this, and this other one is like, let's make it go like that, okay? So first of all, you would plot the line. So I graph the line, which I did up here in black, right? Then what I would do is pick a point not on the line, like 0, 0, and I'd plug in 0, 0. So when I plug in 0, 0, I get 0 is less than or equal to 2 times 0 minus 1. So I get 0 is less than or equal to -1. If that's a true statement, you shade the side with the point. If it's a false statement, you are always shading the side that's true. So if I picked a point and plugged it in and got this, that tells me that 0 is smaller than -1, which is false. That means that this side is false, which means that we always shade the true side, so we're shading this true side. Okay? Okay. Then, for this one, notice there's not an equal sign there. That tells me that we're not including that boundary. So it is a dashed line on the graph. So, yeah. So there's my dashed line on the graph. I just made a dash. I love that. Anyway, again, I'm going to pick a point not on the line. And since 0, 0 isn't on that line, I'm going to plug it in too. I get 0 greater than -1/2 times 0 plus 2. I get 0 is greater than, that goes away, 2. Is 0 greater than 2? The answer is no. So the point that I picked in respect to this purple line is false. So again, you're going to shade the side that's true. If this side is false, then this side has to be true. So this is the shading for this one. Okay? Now, what's interesting, I think, or kind of the result of all of this, is that if I pick a point in here, it won't work with this one. It won't work for this one. If I pick a point here, it's not going to work here in this one. By work, I mean it's not going to be a true statement. If I pick something here, it will work for both of them. If I pick something here, it will work for neither. So this right here, this space right here, is called the solution to the system. Because we have systems of equalities, which is where the one point comes, and we have systems of inequalities, which is a region. All right, so that's what we've done for the last, month. So this is a month recap of everything that we've done. So if you need any help, don't hesitate to email me and I will help you. Okay, bye-bye. Have a wonderful day.